Greetings students and welcome back to my lecture series on topics in ODEs. Today I'm going to continue my lessons on Bessel's equation and Bessel functions by talking a bit about the Bessel function of the second kind. Let's begin this video by reviewing a couple of results. The first result I want to review is that the Bessel function of the first kind of order p could be written as x to the p times the sum from k equals 0 to infinity of negative 1 to the k over 2 to the 2k plus p times k factorial times the gamma of k plus p plus 1 times x to the power 2k. The second result I want to review is the fact that Jp is the solution to Bessel's equation corresponding to the positive root of its indicial equation, whose roots were r equals plus or minus p. Now when the order p is not an integer, or even a half integer for that matter, we said that the general solution to Bessel's differential equation is just a linear combination of j sub p and j sub negative p, where j sub negative p corresponds to the negative root of the indicial equation, which we get by applying the Frobenius method. When p is a half integer, recall that in my previous Bessel equation video we said that the general solution just involves sines and cosines. Now what happens when p is some integer n, like when it's 0 or when it's just some other integer? In that case, you have to consider two possibilities when it comes to finding the second solution to Bessel's equation, which in this case would be the Bessel function of the second kind. The first possibility is when p equals 0, in which case the roots to the indicial equation we solved are repeated. Now you know from my Bessel functions and Frobenius method video, the links in the description, that when the roots to the indicial equation are repeated, the solutions to the Bessel equation you're solving would look like this, with the capital A sub k as a constant to be determined by plugging back into the differential equation and solving the subsequent equations. The next possibility is when p is some non-zero integer, in which case the solutions to Bessel's equation would look like this, where capital A sub k and alpha are constants that once again you have to determine by plugging back into the differential equation. So if we want to find the Bessel function of the second kind, we could just take these y2's, plug them back into the differential equation, and solve for the unknown constants. But most books don't do this. They find or define the Bessel function of the second kind using a slightly different method. They start by supposing that the order of the Bessel function, the p, is a non-integer. In that case, we know that the solutions to Bessel's equation are just j sub p and j sub negative p as we said above. Now, since the Bessel equation is a linear ODE, any linear combination of j sub p and j sub negative p is also a solution. Now, when it comes to finding the Bessel function of the second kind, what we do is we pick a very specific linear combination of jp and j negative p, which looks something like this. This is what we call the Neumann function of order p. It's also a solution to Bessel's equation because for non-integer p, these coefficients involving sines and cosines are just well-defined numbers. Now, how do we get from the Neumann function of order p to the Bessel function of the second kind? Well, we just take the limit as p approaches an integer n. And that limit is going to give us the Bessel function of the second kind, which is also the second solution to Bessel's equation of integer order. Now, here's the thing. As p approaches an integer n, the numerator approaches 0 because of cosine n pi, as well as this property relating j sub n and j sub negative n. And the denominator also approaches 0 because the sign of an integer multiple of pi is 0. Since we have an indeterminate form for our limit, what we can do is use L'Hopital's rule, also known as L'Hospital's rule for the English-only plebeians. So we'll take the numerator and denominator and differentiate them individually, but now it's with respect to p. We are not differentiating with respect to x because x is not the variable we're changing in the limit, it's p. If we take the derivative of the denominator, we'll just have pi times cosine p times pi. If we differentiate the numerator, we'll have to use the product rule on the first part, and just regular differentiation on the second part. Now things should be better because we can directly replace p by n and end up with an answer that isn't undefined or undetermined. Now what happens when we let p approach an integer n? Well, this sign becomes 0, and the cosine becomes negative 1 raised to the power n, which would leave this as our expression for y sub n. All we have to do now is take this expression for j sub n and differentiate it accordingly with respect to n to get the Bessel function of the second kind. I'm not going to do this long, painstaking procedure, but I will provide some hints that might be useful to you. The first hint is that the derivative of a to the u with respect to u is just a to the power u times ln a, while the second hint is just the definition of the di-gamma function, which is just the ratio of the derivative of the gamma function to the gamma function itself. If you use these two hints and apply the product rule to the derivative of j sub n, then after extensive simplification you'll finally end up with this expression for the Bessel function of the second kind of integer order n. And that should do it for this rather short video. If you enjoyed this video, feel free to like and subscribe. This is the Faculty of Khan signing out.